NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will build an intuitive step-by-step algorithm to analyze quadratic equations of the form ax squared plus bx plus c equals 0 when two real roots exist and x2 is greater than x1. We will use signs of c over a, the sum of roots negative b over a, and the discriminant delta to decide where the roots lie on the number line and whether they exist or repeat. Two key facts guide us. By Vieta's formulas, the sum of the roots equals negative b over a, and the product equals c over a. The discriminant, delta equals b squared minus 4ac, tells us whether the roots are distinct, repeated, or non-real. Case 1. If c over a is less than 0, the product of the roots is negative, so the roots must have opposite signs. That means x1 is negative and x2 is positive. Now, compare the sum negative b over a. If the sum is positive, the positive root must dominate in magnitude. The absolute value of x2 is greater than the absolute value of x1. If the sum equals 0, then b equals 0, and the equation is symmetric x equals plus or minus the square root of negative c over a. If the sum is negative, the negative root dominates. The absolute value of x1 is greater than the absolute value of x2. Case 2. If c over a equals 0, then c equals 0. The equation factors as x times ax plus b equals 0. So one root is 0, and the other equals negative b over a. Important note on special relationships. If c over a equals 1, then the product x1 times x2 equals 1, meaning the roots are reciprocals of each other. If c over a equals negative 1, then x1 times x2 equals negative 1, so the roots are opposite reciprocals. Case 3. If c over a is greater than 0, then the product of the roots is positive, so the two real roots, if they exist, must have the same sign. To decide further, we examine the discriminant delta and the sum negative b over a. If delta is greater than 0, there are two distinct real roots. If the sum negative b over a is positive, both roots are positive. If the sum is negative, both roots are negative. If delta equals 0, there is a repeated real root. If the sum negative b over a is positive, that repeated root is positive. If it is negative, that repeated root is negative. If delta is less than 0, there are no real roots. In this example, we will determine for which values of the quadratic equation x squared minus 2 ax plus a equals 0 has two distinct positive roots. We'll build the conditions step by step, visualize them on number lines, and intersect the results to find the final answer. For the quadratic x squared plus bx plus c equals 0, our coefficients are a equals 1, b equals negative 2a, and c equals a. To have two distinct positive roots, we need three conditions. First, the discriminant is positive. Second, the sum of the roots is positive. Third, the product of the roots is positive. Start with the product condition. The product of the roots is c over a, which here equals a over 1. For two positive roots, the product must be positive, so it is greater than 0. We will call this domain D1. Next, the discriminant must be positive. The discriminant is b squared minus 4ac. Here, that is negative 2 a quantity squared minus 4 times 1 times a. That simplifies to 4 a squared minus 4a, which factors into 4 a times a minus 1. For this to be greater than 0, a is less than 0 or a is greater than 1. We will call this domain D2. Finally, the sum of the roots must be positive. The sum equals negative b over, which is negative of negative 2a over 1, that is 2a. Therefore, the sum is positive when it is greater than 0. We will call this domain D3. Let us visualize D1, D2, and D3 on number lines, and then intersect them. We will stack four number lines, D1, D2, D3, and the final intersection at the bottom. First, D1 is from 0 to infinity. Next, D2 includes a less than 0 and a greater than 1. Then, D3 is again 0 to infinity. Intersecting all three gives 1 to infinity. Algebraically, the intersection is D equals D1 intersect D2 intersect D3, which simplifies to the interval 1 to infinity. Therefore, a must be greater than 1. As a quick check, choose a equals 2. Then the equation is x squared minus. Example, if the equation ax squared plus 2x plus a squared equals 0 has two real roots of opposite signs. Find the range of a. Step 1. For a quadratic, ax squared plus bx plus c equals 0, having roots of opposite signs, means the product of the roots is negative. The product equals c over a, so the condition is c over a is less than 0. Step 2. In our equation, capital A equals a and capital C equals a squared. Substitute into c over a is less than 0. That gives a squared over a is less than 0. Step 3. Since a squared is always non-negative, the fraction a squared over a can only be negative if the denominator is negative and it is not 0. So the inequality reduces to a less than 0. Step 4. Consistency check with the discriminant. The discriminant for ax squared plus 2x plus a squared equals 0 is delta equals b squared minus 4ac, which is 4 minus 4 cubed. For a less than 0, a cubed is negative, so 1 minus a cubed is greater than 1, making the discriminant positive automatically. Therefore, opposite signs with real roots is fully satisfied when it is less than 0. For intuition, let us visualize one example with it equals -1. The function becomes negative x squared plus 2x plus 1. Because it is negative, the parabola opens downward. It crosses the x-axis at 2 points with opposite signs. Recap. The condition for opposite signs is c over a less than 0. Substituting a equals a and c equals a squared gives a less than 0. The discriminant is automatically positive for negative a. Final result is less than 0. Negative a. Final result is less than 0. In this lesson, we will analyze the roots of a quadratic without solving it explicitly. Our equation is -100x squared plus x plus 57 equals 0. Our goal is to discuss existence and signs of the roots, and which root has the larger absolute value. First, identify the coefficients. A equals -100, b equals 1, and c equals 57. Next, recall Vieta's formulas for a quadratic ax squared plus bx plus c equals 0. The sum of the roots equals -b over a, and the product of the roots equals c over a. Let's start with the product of the roots. We compute c over a. That is 57 divided by -100, which is -0.57. Because the product is negative, one root is positive, and the other root is negative. Now, let's analyze the sum of the roots. -b over a equals -1 over -100, which is 1 over 100, a positive number, with one positive root and one negative root, and the sum positive. The positive root must have the larger absolute value. Let's also look at the graph for intuition. Since it is negative, the parabola opens downward, with y-intercept at 57, and the vertex slightly to the right of 0 at x equals 0.005. The graph crosses the x-axis in two places, one negative, one positive, matching our sign analysis. To summarize, the product of the roots is negative, so the roots have opposite signs. The sum of the roots is positive, so the positive root has the larger absolute value. We reached these conclusions using Vieta's formulas without solving the quadratic. In this lesson, we will determine the existence and the sign of the roots of a quadratic without actually solving it. We'll use the discriminant and Vieta's formulas to reason visually. Here is our example. We will analyze the equation shown in orange and decide whether its roots exist as real numbers, and if so, whether they are positive or negative. Step 1. We check the discriminant to see if real roots exist. The discriminant is delta equals b squared minus 4ac. For a equals 5, b equals 35, and c equals 2, delta equals 35 squared minus 4 times 5 times 2, which is 1,225 minus 40 equals 1,185. Since delta is greater than 0, there are two distinct real roots. Step 2. We use Vieta's formulas to study the signs. The product of the roots equals c over a. For this quadratic, c over equals 2 over 5, which is positive. A positive product means the two roots have the same sign. Step 3. The sum of the roots equals -b over a. Here, that is negative 35 over 5 equals negative 7, which is less than 0. Since the sum is negative and the roots share the same sign, they must both be negative. To visualize the sign conclusion, in this video, we will solve a quick but powerful algebra problem using a very visual approach. Find the value of t so that the quadratic equation x squared plus 4x plus t plus 2 equals 0 has two reciprocal roots. To organize our thinking, let us place the equation next to the general quadratic form and recall Vieta's formulas for sums and products of roots. We will identify a equals 1, b equals 4, and c equals t plus 2. Then by Vieta, x1 plus x2 equals negative b over a, and the product x1 times x2 equals c over a. Reciprocal roots means x1 equals 1 over x2, which is equivalent to saying the product of the roots is 1. So x1 times x2 equals 1. Comparing with Vieta's product, we set c over a equals 1. Since it equals 1 and c equals t plus 2, c over a equals t plus 2 over 1. Therefore, we must have t plus 2 over 1 equals 1. This simplifies to t plus 2 equals 1. Solving for t, subtract 2 from both sides to get t equals negative 1. So the required value is t equals negative 1. Let us quickly check. If t equals negative 1, the equation becomes x squared plus 4x plus 1 equals 0. For this equation, a equals 1 and c equals 1, so the product of the roots is c over a equals 1, as required. Our result is consistent. The question is, find the value of t such that the quadratic equation x squared plus 4x plus t plus 2 equals 0 has two symmetric roots. When we say two roots are symmetric, we mean they are opposites around 0. Picture a number line, one root at a positive distance a and the other at negative a. Their sum must be 0. For a quadratic x squared plus bx plus c equals 0, Vieta's formula says the sum of roots is negative b over a. For symmetric roots, the sum is 0, so negative b over a must equal 0. That means b must equal 0. Now apply this to our equation x squared plus 4x plus t plus 2 equals 0. Here a equals 1, b equals 4, and c equals t plus 2. The requirement b equals 0 is impossible because b is 4. So there is no value of t that will make the roots symmetric by the sum condition. Let us also see this visually. Consider the graph of y equals x squared plus 4x plus t plus 2. The axis of symmetry is at x equals negative b over 2a, which is negative 2, and does not depend on t. Changing t just shifts the parabola up or down, but never moves its axis to 0. So the 2x-intercepts, when they exist, cannot be symmetric around 0 for any t. Conclusion, there is no value of t such that x squared plus 4x plus t plus 2 equals 0 has two symmetric roots. The horizontal position of the parabola is fixed by the coefficient of x, and t only moves the graph up or down. In this example, we will find the value of t so that the quadratic equation x squared plus 4x plus t plus 2 equals 0 has a double root. We will solve it algebraically using the discriminate and then confirm the result with completing the square and a graph for intuition. Step 1. A double root means the two solutions are identical, so the discriminate is 0. In general, delta equals b squared minus 4ac. Because b is 4, which is even, we can also use the reduced discriminate. Delta prime equals b prime squared minus ac, where b prime equals b divided by 2. Step 2. Identify the coefficients from the quadratic. Here, a equals 1, b equals 4, and c equals t plus 2. Substitute into the reduced, discriminate equals 0. 2 squared minus 1 times the quantity t plus 2 equals 0. That simplifies to 4 minus t minus 2 equals 0. Combine constants to get 2 minus t equals 0, which gives t equals 2. Step 3. Let us confirm by completing the square. X squared plus 4x plus t plus 2 equals the square of x plus 2 plus t minus 2. A double root means the expression equals a perfect square touching the x-axis, so we need t minus 2 to be 0. That again yields t equals 2, confirming our solution. Finally, let us see the geometry. We draw axes, and the family of parabolas y equals the square of x plus 2 plus t minus 2. For t less than 2, the vertex is above the x-axis. When t equals 2, the vertex sits on the x-axis at -2, 0, showing the double root. For t greater than 2, the whole graph shifts upward, and there is no real root. Therefore, the value of t that makes the quadratic have a double root is t equals 2. In this lesson, we will find all values of t for which the quadratic equation x squared plus 4x plus t plus 2 equals 0 has two negative real roots. We will translate this question into 3 simple conditions, check each condition for our specific coefficients, and then combine the results on a number line. For a quadratic ax squared plus bx plus c equals 0 to have two negative roots, 3 things must be true. 1. The product of the roots is positive, which is c over a greater than 0. 2. The sum of the roots is negative, which is minus b over a less than 0. 3. The discriminant is positive, so b squared minus 4ac is greater than 0. In our equation, a equals 1, b equals 4, and c equals t plus 2. Let us plug these into the 3 conditions. First, product positive gives t plus 2 greater than 0, so t greater than -2. Next, sum negative gives minus 4 less than 0, which is always true, so it adds no restriction on t. Finally, the discriminant b squared minus 4ac greater than 0 becomes 16 minus 4 times t plus 2 greater than 0. That simplifies to 8 minus 4t greater than 0. So t less than 2. Now we combine t greater than -2 with t less than 2 on a number line. We mark an open circle at -2 and another open circle at 2, and shade the interval in between to indicate all t strictly between these values. Therefore, the final answer is -2 less than t less than 2. In this example, we will find the parameter t so that the quadratic equation has a root equal to 0. We will use 2 clear ideas, identifying the constant term and the product of roots property. Step 1. Write the standard quadratic form and match coefficients. Here at equals 1, b equals 4, and the constant term c equals t plus 2. Step 2. If 0 is a root, substitute x equals 0 into the equation. The x squared term and the 4x term vanish, leaving only c equals 0. Therefore, c must be 0. As a quick cross-check, the product of the roots equals c over a. If one root is 0, the product must be 0, which again forces c equals 0. Step 3. We already matched c equals t plus 2. Setting c to 0 gives t plus 2 equals 0. Solving yields t equals -2. Step 4. Let's check quickly. With t equals -2, the equation is x squared plus 4x equals 0. It factors to x times x plus 4 equals 0, so the roots are x equals 0 and x equals -4. We can visualize that on a small graph. Final answer, t equals -2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.